introduce our special guests, Professor Dan MacIsaac and Professor Kathleen Falconer from State University of New York College, sunny Buffalo State, USA. The topic is analyzing physics teaching video and the reform teaching observation protocol. So we'd like to inform that you have 30 minutes for your presentation with question and answer. Now I would like to give this floor to the speakers. Thank you.
Welcome. Good morning from Germany.
Good morning, sir.
Good morning. So I am Dan, and this is Kathleen. We are a married couple who are also physics education researchers. We work with pre-service teachers mostly. I run 2 master's programs at SUNY Buffalo State College in New York, where I've worked with over 350 teachers to date who are all physics teachers. And Kathleen is a doctoral candidate at Universität zu Köln in Cologne, West Germany. And we publish together.
Wissenschaftliche.
Our presentation here is online, and we're going to show a video as well during the presentation. And we would like you, when you're watching the video, to make some notes and write down your ideas and drop your thoughts into the chat box. Ordinarily, this is part of a much longer workshop where we spend a lot of time discussing what we see and don't see in the videos, but it's a nice time. I know it's at the end of the day for you, so you're kind of tired, but you get to watch someone else teach and criticize it. So it'll be great, right? I mean, who doesn't like that? And hopefully we can negotiate some ideas about science teaching and physics teaching in particular. Okay, so this is our first slide. We will be spending most of our time looking at the physics videos. We will allude to this tool that does a formal treatment of many of the ideas. This is how to get in touch with me and Kathleen. And these slides are available online. So we have been doing this for several years now, 21 years now. And these videos have been around and are well known in the English speaking community. So we have a rather rich video here of some people teaching, and we want you to look at it. It's a 13-minute long video. It's in English, so it's not fair. It's too short and it's not in your native language, but that's okay. We're just going to look at it and see what you can figure out about the teaching and learning that are going on in the room. And then we're going to discuss it. And I hope that'll be an interesting video and provide you with some insights, some interesting things to talk about. This video, you can get it yourself. It is on my YouTube channel. You can actually type my name, MacIsaac, and YouTube, and you will find me. Or this is a direct link here to this video. It's actually called RTOP 4, Modeling via Intensive Student Discourse. Okay, we're gonna, yes, yeah. So here are your questions. So this is, I will state that it's a very successful classroom. The students are shown by pre and post testing that they learn a lot. And it's very non-traditional, even for Americans, okay? It's non-traditional everywhere. So I'm hoping that you will enjoy it. So the questions I have for you, and I suggest you pull out a piece of paper and a pen and write down some notes as you watch this video. What's going on? What's happening that you think is promoting learning or not? And if you see interesting behaviors, comment on them, okay? Particularly if you think they're promoting learning. Okay, so let's watch the video. Just to tell you a little bit about the video, the students have been told that on the last day of class, when they come in, they're going to actually study how a ball bounces. So that's how a ball bounces. And that's all they've been told. So you're going to watch them come through the door and start on that task. Good.
bounds.
So it was just a constant.
It's a sign. Your velocity is going to be. It's going to be something. It's going to be. So the velocity is a constant. So it's going to be. So it's going to be. Well, okay, and at this point, it's going to reverse its direction. This is where it
It's going to reflect smaller.
counts. This is where it goes over the top and reverses direction again. But
It's coming back right now. It's negative, but it's slowing down. Yeah. So when it comes up, it's going down. It goes down. So it'd be like. Yeah, but one day would be like up and then back down. You think so?
So we're at
Yeah, that's about what we
a
did.
little lower than negative 15 because we got an instantaneous. But I got a question for you.
Yeah, but that was pretty close. Yes. Trust me, I'm pretty good at that.
Okay. The first thing I'm going to point out to you guys that you have to worry about. I'm just going to use my little tool here so I can
Yeah.
get my pictures at the same time. Okay, looky here. Our acceleration goes from its constant right at that point right there. Do you agree with that? But what direction is the ball still going? Where?
Still going up.
When the
or down.
velocity is here, it's still going down. Yeah, in fact, it doesn't reach its furthest point until it's clear there. Right where velocity equals zero. Right. Notice, what does it mean when all of a sudden the acceleration goes from constant? What's happening? That's the ball where the ball hits the what? There's compulsion. Oh, so is the particle model going to work?
No.
You got to turn back. We can use a little squishy particle. What we can use tomorrow with that?
It's kind of straight. It's trying to be straight.
It's pretty much.
because the ball's like.
Yeah, kind of wobbling.
It's
And
just, but where does it? According to the acceleration, where does the acceleration change? Where would I move this to show where the first acceleration changed?
right down.
Right.
Right about there.
Yeah, when it
A little bit
makes this
over, a little bit
steep
more.
slope down.
Which direction is the ball still going?
Still going. That's the point where it's like changing.
What can we do to add to it? What do you guys have to add to what they said? Plate type thing, like this. And we got the same. Our ball was the same as yours. The spring,
Right.
with two particles on each side, or one on each side. And we modeled the ground as a rectangle type thing with particles inside. Each one of those particles can freely move. And basically we modeled, we already knew the motion of the ball. So we modeled what's happening inside the ball and why it's doing what it's doing. And in doing that, we got our motion / energy map. I don't know what you want to call it. But basically, at the top, you have what's called energy interacting, and that's energy that is brought by gravity, or the interaction between the ball and the earth. And as it moves down, you gradually move to kinetic energy, which is energy of movement. And halfway down, you're going to have half EI and half EK. And EI is energy interacting, and EK is energy kinetic. As you get closer down, you get closer and closer and closer to all EK, which is kinetic energy. And right before it hits the ground, you have basically all EK, and just a very, very, very small amount of interacting. Then when it hits the ground, like they said, it compresses. And you have a new form of energy, which we call, where is it? energy internal. Okay? And that is energy, he doesn't want me to use this word, but it's like,
No, use it then.
It's the energy that's absorbed by the
it's
ground
moved,
and the ball.
it's displaced energy, reacting energy at its most compression point, and transfers back over to kinetic energy again.
But I think every time you hit the ground, your internal energy is going to get bigger.
You're right.
And then finally, it'll just be all internal energy. Because
So-
it's going to stop bouncing.
Right. And then as you go back up, the internal energy gets more and more as the kinetic energy gets less and less. And it repeats until eventually the internal energy encompasses the entire charge. What?
Okay, maybe it's just me, but that's a whole lot more confusing than just a ball bouncing.
Well, just like if you have a ball just sitting there, it's not interacting. But if you like hold it up, then that's interacting because
Right.
you're doing the work. You know,
So-
you can actually interact if you just drop off like the ball. It can just start hitting, then that's an interaction. Then you're putting the work.
Yeah.
Does that make sense?
When it's sitting on the ground, wouldn't there still be interacting though? Because basically the ground is
Not if
holding
there's
it
not
up.
an outside.
The ground is holding it up though.
I don't want to say force, but not
Yeah.
if there's not an outside person or whatever energy.
So wait,
I,
what are you
Does that make
saying?
sense?
I would
It
just,
should
I would
be all
still picture
interacting
that as
energy at the
interacting.
bottom?
Yeah, like
Yeah.
there wouldn't
That's
be
what I-
any mysterious internal because that doesn't make sense to me.
The internal energy, I think, comes from after.
The bounce.
I mean,
but
There's some
always-
internal energy the second it hits because the particles in the ground start moving. That's
Right.
internal energy.
Well, the particles are still moving while it's inside, even when you're just holding it still. I mean, there'd still be
Yeah.
internal energy there.
So you can't
Yeah.
just say that
I know that.
the interactive energy here, and then after it's done, is going to be the same because you've hit the ground. You've
Well,
moved the
I
particles, so
think
it's
what
not
I'm
going to be the
saying
same.
is it
I'm
does
aware of
go
that.
back, but it's. Go ahead.
The way that your model is, you don't show any interacting energy in the ground itself. You show it all in the ball.
No, that's what.
That's
this
why
is.
they're moving faster.
That's why we have arrows because they're moving now.
What is this particle connected by a spring model representing?
Oh, right.
He said it's representing the ball, so if we have,
It's representing the
like
particles
he was
inside
saying,
of the.
there's still the action there. If you have one particle, there's no action in that particle. It's a single particle. So if it's not moving, when it's sitting there, then that's the internal energy.
A, where you're holding the ball. B, you got the ground. And if you have a ball, whether it's a lead ball or whether it's that ball, there's going to be different amount of internal energy. A lead
Yeah.
ball is going to go boop, little bounce and stop. So there's different kinds of energy in each ball because our springs are different in each ball.
Yeah.
That.
Because that's the model we're using.
I completely understand
So it's
that.
not changing the particle, it's changing the model we're using
Okay,
to
but I'm
describe
hearing
this
it's
section.
changing the particle.
Okay,
No,
I
okay.
That's
think
not
the
what we're
question
doing.
that's being asked is.
Okay.
I didn't say
I
we're
mean,
changing the
sorry.
model of which section of the axiom we're describing. The first section, like you were saying, we had the first section particle. The floor, then that's the next model would be the spring and the other particle because we have to describe the compression between the two. And then after
And
that,
then
we can go
after
back
that,
to a
it's back to our
model, we're not
original
changing it.
model.
Because in that last section, all we're talking about is the movement of the ball going back up and then falling again.
Does everybody agree that this guy has, if we're making a better model than we are right now, does this guy have particles in it?
Yes.
Are they moving around?
Yes.
Okay. So we're just pretty much ignoring that. Does everybody agree with that? Is that a fair thing to do? Okay. Okay. So it comes down, what happens on its way down?
Building, building energy.
Some of that energy changes.
It transfers.
It transfers, okay? I'm going to kill a word right now that I've heard a few times, so I didn't step in. There is no forms of energy, okay? There's only one energy, okay? There's only one energy, and it's stored in different places. So it's one form, different ways of storing it. It's like having a dollar bill and a dollar bill versus quarters.
The ground, so it has to be in the ball. It's already been
It's
given
in
to
the
the
ball.
ball. Once the ball leaves the ground's not participating until the ball comes back down.
So, look at this idea and keep it in mind. Now, you said one other word and you said it in passing. I got 2 minutes to come back to it. I'm just going to write it on your guys' board here in the middle. And Mangle is out of tape. Okay? System.
Okay. What? Okay.
Slides or something.
Right over there. You just missed it.
Okay, so everybody saw the video. It's about 13 minutes long. It's a pretty famous little clip. So what did you see? I saw a pile of comments here in the chat. If you want to unmute, raise your hand and we'll unmute you. Or you can put your comments into the chat. Either one are fine. Yeah, I think the students did do a good job in this class. The boards aren't very difficult to make.
They did a nice, the students' whiteboards are very practiced.
Yes, the students have a great deal of practice and familiarity in using these whiteboards.
Did they figure out who the teacher is?
Did you figure out who the teacher was? It's a little hard because he looks so young and doesn't speak so very much. But someone commented that the students were doing most of the speaking, and that is in fact what we try to promote. We claim that the person doing the most talking in the room is probably doing the most learning. So if it's the teacher, that might not be the best use of the opportunity for learning if we want our students to do the learning. Okay, so we have a slide here that talks about this. So there's roughly 3 sections to the video, and you're welcome to continue to comment in the chat. So there are roughly 3 main sections to the video. There's a student data gathering activity. They come through the door and start on that. And clearly they're very used to doing that. They're not shy at all about doing it. They go right to work. Then there is a, yeah, they focus. It is very much like problem-based learning. Good observation, absolutely. And they're really problem-driven. And someone said, it looks easy, it's not. And they do put a lot of pressure on themselves. So, but they are having fun, nonetheless. So they have a data gathering activity where they collect data at the beginning, and then they get in a circle where they try and discuss their data. And you see the discussion that we call it circle whiteboarding. The little boards are called whiteboards, and we cut them out of a common scrap material in the US. And then it ends up with the teacher doing a very short section, warranting knowledge, saying that this is so, that is not, this is important, that is not important, and then sets up the next activity, which will be something on systems. And his comment, the other thing you should know about is that in a regular classroom, whether it's a 1-hour or 2-hour classroom, those are about the right proportions for these activities. Okay, that the students spend a lot of time talking and a lot of time gathering data. And they tend to listen more to the teacher because the teacher talks to them a lot less. So when the teacher does speak up, it's very valuable to them. What do we go? Okay, so the first section, student data gathering. They enter class, go right to work, model how a ball bounces. And you heard them use the word modeling a lot. That's really important in the next generation science standards. In the US, yes. The students are obviously comfortable working in groups and on their own. They have tools, or what I call hammers. They have a whole bunch of hammers. One of them is to use sonar and make plots, XVA plots, which actually aren't very helpful for this problem, but they know how to do that and they do it. Okay, so they have their hammers and the world is a nail. So they're gonna take the hammers to the nail. So they make these plots, but what you kind of hear in the background and you see once is the teachers moving around the room, pushing each group in a slightly different direction. And some of them are being given valuable parts of the puzzle that talks about how the ball bounces. Okay, so different groups get different questions. And the teacher did come in and ask, you know, what's happening here? What direction is the ball moving in? And you heard the students struggling with that. And some of the groups, when he went around the room, he gave them a new tool, this idea of a circular pie chart with energy. So in the circle, when they got back, only some of the groups had this new tool, this circle. And they were the ones that were asked to speak the most, or wound up speaking the most. Okay, so the second section of the video is this circle whiteboarding. And there's a lot written on circle whiteboarding. And we can refer you to it, or you can find it just by Googling it. The modeling physics method use it and trains pre-service and in-service teachers in how to do this. But in circle whiteboarding, the students are clearly trained in taking turns and listening to each other, and they practice shutting up. It's really hard to shut up, especially for teachers. You hear lots of the word model being used, explicit use of model building. They decide that while they're in their circle, they're going to use two objects separated by a spring as their model. They have a new tool, which is this energy pie chart, and that gets significant billing. And there is jargon control. The teacher does want them to use certain language and not other language. And you did notice that when he stepped into the circle, he had to step into kill a word. He didn't want the students talking about forms of energy. And so he thought that that
transfer.
was- yeah.
Transfer is the important part.
Yeah, he wanted transfer of energy from one bin to another, from one storage mechanism to another. So he felt very strongly about the word forms of energy. And it's really common in this kind of instruction to ask students not to use particular words until everyone knows what they mean. A real common one is force when teaching mechanics. You don't want the students using force or angular momentum or some new buzzword without understanding it, and forces them to go back and makes them go back and think harder about what they're learning. And then he wants them to use particular words like system. Okay, so some words he kind of approves of, and other words he kind of disapproves of. So he's trying to focus their thought by their language. And that leads us into the warranting section. There is an advanced language control, there's a vocabulary manipulation. Sometimes you'll even see teachers and we train them to write words on the board and draw a line through them. And those are your verboten words, your forbidden words. He does limit closure. It does have a closure at the end, but it's still very open-ended. They're still thinking about stuff as they go into the next activity. And so it's a sharply limited closure. And he does force agreement on some things where he doesn't want the students spending too long in that blind alley. Okay, some overall comments. It's a strongly meaning-centered class. It's highly motivated and on task. Some of you commented on that. There's a sense of student control and empowerment. Whether that's real or not is another story, but it's a sense of it. Student discourse is intensive. It's all about the student talk. It's Vygotsky. The instructors manipulated the activity and the environment. For instance, the balls have all been partially deflated. He took the air out of the balls so that they didn't bounce very well. So he's extensively messed with the environment in which they're working. And then they are apparently free to go through it on his questions. So it's very Machiavellian, we call that. He is controlling them, but not by making them
Overt.
A covert control over the learning environment is what's happening. And hopefully you will see much more prediction and testing in future things. So there's a bunch of references here on this. The video is available, and there is a way to assess what's going on this way in the classroom, and that's the RTOP, the Reformed Teaching Observation Protocol. There is an article here in the physics teacher on it. You can contact me or look me up on ResearchGate and get a free copy of that. It has been translated into Chinese. So if you would like a Chinese copy, I can give you that. It has not been transposed into Cambodian or Thai, but it has been translated into Chinese. So, and they're working with it right now in China. Any questions or final comments?
And we stopped exactly.
So yeah, we would like to say thank you so much for incredible presentations and even incredible video. So because of the time limitation, so now it's time for question and answer. And I would like to remind you again that all the participants can drop your question in the chat box below. So we welcome all of your questions.
I think the time
Okay, so there is a question. In Cambodia context, it is difficult to create a safe space of sharing ideas for students. Do you have any recommendation to motivate students to share what they thought?
You do it slowly. You don't expect it to happen immediately. One of the things that I've found is that you say that the room will be a safe environment. You give them autonomy within the room, which the first time it happens, they're kind of shocked sometimes. But you have to decide what level is good for you, okay? It takes time, and you just need to be persistent. You need to help them to ask questions at the beginning. They will get better at it, okay? This is not something that's going to happen the first day, the first week, or even the first month, okay? So you just have to keep going. Now, there was a question about the real result. The question is, when do they need to know the correct or scientifically accepted answer? It's not necessarily at the end of the class, but it's might be a week later, right? And sometimes it's very important for them to go through their understanding and their misconceptions and their ideas that are not conducive to the scientifically accepted model, to say, okay, this model works in this context, this model works in this context, and I feel self-confident enough to know that I let the students work on this, and then I know that we are going to get to the stage where they confront their lack of understanding, and then they go, oh, and the aha moment happens and they do it. Is there anything else?
So, yeah, there are more questions. So, but I see that you are writing in the chat book, but I just would like to read the question, and you might read it so that participants can hear it better. So the question is, how the video of experiment help teacher in teaching science in classroom with blended learning?
I don't see that one anyway.
Right there. What do you mean by blended learning? That's a word that has lots of different meanings depending upon where it's being used at.
Okay, so because the participants could not ask the question clearly, so I would raise another question. That's how will teacher do if they do not get the real result?
No, I'm just asking what they meant by blended learning, because blended learning can mean lots of different things. I actually think that it's, again, it's the whole idea of going slow. Your job in the classroom looks like you're not doing very much work if you're doing this right. You look like you're not doing very much at all, but you're actually doing a whole lot of stuff. I take notes constantly about what the students are talking about, what they're thinking, what their ideas are at that particular point, so that I can go back and make sure that we do an experiment or an activity, or we ask the right question so that they can, if it doesn't come up from them, that it comes up from me. Okay.
So I'm sorry to interrupt. So thank
we're
you
out
so
of
much
time.
for thank you so much for question and answer. But however, because of the time limitation, so would you mind to answer the remaining question later, Professor?
Actually, I think I already did. I put it into the chat.
Yes, sir. So thank you so much for today's presentation and incredible videos. So we hope that all the participants can get the concept or ideas of what you have present today. So we thank you so much. So now you could have a relax. So thank you, Professor. So hope to see you next time, Professor. Yeah. So
you.
yeah, thank you so much.